Hello, everyone, and welcome to this webinar on Advanced Reconstruction Toolkit, leveraging AI to solve X-ray imaging challenges on ZEISS Xradia platforms. We have quite a lot to get through today, so I'm not going to hang around waiting for too many people to join. Looks like there's already a fair number of people joined. But yeah, so without any further ado, I'm just going to get started on the presentation. Just a little bit of housekeeping as we start. Please make sure you are muted during the presentation, and also do make sure your camera is off just to avoid distractions. Any questions that you have during the presentation today, if you just submit them via the chat function, towards the end of the presentation, we will address as many of the questions as we can in the time frame that we do have. Yes, please do actively use this chat function to ask questions or just to make general comments. This will all be saved towards the end of the presentation, so any questions that aren't answered today, we will endeavour to get back to the person who asked the question and answer your question thoroughly. So, what are we going to be looking at today? So, we're going to have a very quick introduction to what X-ray microscopy is at ZEISS, to give a bit of background to what ART, Advanced Reconstruction Toolbox is. We then will go through the different components of the Advanced Reconstruction Toolbox. The last section is actually a conclusion, not a demo. Apologies for that mistake. So, moving on swiftly to what is XRM at ZEISS. So, just in case, I wasn't quite sure of the audience today, so just in case, a very quick introduction on what 3D X-ray CT is basically. So you have an X-ray source, you have your sample in the center, and you have a detector of some description at the end. And for the actual tool, you rotate your sample and you take slices, and this gets you a projection data set such as this. Once you have your projection data set, you can then use some clever algorithms to reconstruct that data set in 3 dimensions. And this allows you to look through your samples in detail via via virtual slices. As you can see on this video here, we're able to really go through this sample in any which direction we want once we've completed the reconstruction. And then the final step really is that you are able then on this 3D data set to do quantitative analysis. And obviously this is a non-destructive method as well. So your sample remains intact after you've done a 3D tomography scan, which is fantastic. Just in terms of what we offer at ZEISS, just as a very quick background, is we offer 3 systems for X-ray scanning in research applications, and they are all part of our Xradia range. The first on this side here is the Xradia Context. So this is a standard, I say standard, it's a high performance flat panel X-ray CT. And it is built on the robust platform that was designed for our next tool, which is the Xradia Versa. This is a true X-ray microscope with an ultimate resolution of 0.45 microns, but also almost more importantly really, is it has resolution at a distance, which is enabled by its 2-stage geometric and optical magnification capability. So you can still get high resolution when your sample is further away from the source or when your sample is larger. And then the final part that we have in our Xradia range is the Xradia Ultra. So this is our nanotomography tool with synchrotron style optics, and it's for ultimate resolution of 50 nanometers or less, but only on small samples. So this gives you a little background that will help set the scene for what Advanced Reconstruction Toolbox is. So we have lots of different aspects that we could have decided to work on. So one obviously is the hardware, and that will always go, there'll always be incremental improvements year by year, but that's not what ART is focused on. We also have how you set up a scan. So we have made improvements here, but that is not what advanced reconstruction is about. And then there's also the data analysis. So in a way, one of the most important sections, which you can do by things like Dragonfly Pro and Fiji, but again, not the focus of this. We slot in around about this sort of section here. So it's on the actual reconstruction. So once you've acquired your projections, it's how you're reconstructing those to get the most accurate data. And the Advanced Reconstruction Toolbox is a set of technologies that enables enhancement in the X-ray performance and the subsequent analysis. So these can improve things, throughput, the actual image quality, really the ability to segment your data, but also there is possibility to improve resolutions over large fields of view as well. So you'll notice that I say on here ART 3.0, so it's now in its third iteration. And this is the majority of the lineup that we have in terms of modules for ART. So the first one is Deep Recon Pro. So this is applying a deep learning neural network for reconstruction that allows a throughput increase of up to 10 times, but also has significant improvements in the image quality. So the change from the previous version of ART is that we can now do this for Xradia Ultra data. The first entirely new module for ART is one called Deep Scout. So this is using, again, deep learning neural networks to basically apply a small volume, high resolution data set and apply this to a large volume, lower resolution data set. So significantly increasing throughput, but also enabling you to apply high resolution to a much wider range in a much reduced time. The other two components are not AI focused, but nonetheless are very useful. So we have phase evolve. So when you're working in phase contrast mode on our microscopes, which is possible, it's a software tool that allows you to remove the fringes that are inherent to the phase contrast mode that we use. So very useful for getting segmentation on samples where the density difference in your materials is quite low. And then the final one to mention is MARS, and that stands for multi-material artifact reduction. And this is actually almost the opposite of phase evolve. So it's when you have very high density differences in your samples, which causes artifacts, and MARS is enabling you to reduce the number of artifacts. So I'm going to actually start from the other end. So we're going to start with MARS because it's the most simple one to explain. So when you have a metal in something like a polymer, you typically see artifacts in the images due to the high density materials. And this is because of nonlinear attenuation in the lab-based X-ray sources. So essentially you get things like dark bands or you get streaks, etc. And what MARS allows you to do is it allows you to reduce these, and it's based on a mature algorithm, which is known as empirical beam hardening correction. It's a very simple workflow. So it's basically when you want to reconstruct, there's a little tick box that says MARS, and you tick that, and it will then optimize your imaging, and it works best when you have a full field of view tomography. But as you can see between this HTML connector, which was imaged at 160 kV, you can see there's a significant reduction in the number of streaking artifacts, and there's smaller reduction in the dark bands that you have between the high density metal solder points and the material, the lower density material that's in between these. So you can sort of use MARS in two ways. So this is a HDMI connector, so it looks very similar to the sample from before. So on the top example we have here, so we've used the same settings with the same filter. So the HE is a filter. And the number here basically stands for the thickness of that filter. And what we can do is we can get better image quality across the same conditions, or you could use MARS to actually improve the throughput of the scan. So you can see here that we have a thick filter before the X-rays get to the sample, or we can use a lighter filter and still get much improved result with MARS. And you can see if using this thinner filter here, when you compare the two side by side, it's a very significant difference indeed. So you can use it in two ways, for better image quality or for improvement in throughput of your sample. So that shows MARS very quickly. So very simple workflow, and quite simple in what it does. If we move next on to phase evolve, so as I mentioned before that we can do something called phase contrast imaging on the Versa and the Ultra platforms. The Versa platform in particular is based on a phenomenon called propagation phase contrast. So what we're essentially doing is it highlights the edges by the different travel speeds of the X-rays when they're passing through an interface. And what this does is it makes the individual different phases much more distinct, as you can see from this graph here. But it does also introduce artifacts in your imaging. So you can see you have a very high sort of gray value followed by a very low one, which makes segmentation of these data sets very difficult for a computer. So whilst obviously the human eye can see very clearly the different phases, for a segmentation software, that becomes quite the challenge. So the phase evolve is designed to solve this problem. So we've got this same data set with the standard reconstruction, and what phase evolve does is it allows you to sort of even out the either ends of the phase fringe and apply it across the whole phase where it's applied, and it gets you a much more uniform grayscale across each sample with a bigger difference in the grayscale as well. So this means subsequent segmentation of your data is going to be much more accurate and give you much better results going forward in something like a paper or a review. So this is just a quick look at what the interface for phase evolve looks like. So you can see it's anyone who has an X-ray instrument already will be familiar with this. For those who are not, this is the Scout and Scan user interface. So phase evolve is just a small window that's part of the Scout and Scan user interface, and then you can load your data into the reconstruction filter, and you can play around with the settings. It does take a little bit of getting a little bit of trial and error in the first instance, but ZEISS has done many examples of this, so we can always help you with your getting the perfect conditions to get the best out of the phase evolve reconstructor. But as you can see, it's a very simple user interface, and what we're really trying to do is level out the peak and the trough between the two different phases. This final example here for phase evolve, this is some poplar wood. Again, a typical use case where the wood itself does not have that much density difference to the surrounding material. You can see on the left-hand side, we have just a standard FDK reconstruction of our data. And you can see, it's still a very good scan, but just because of how FDK works, there is some noise within this data that would make the reconstruction quite difficult. And you can see a bit more difficult on here, but you can see the phase fringes between the wood and the surrounding material as well will make it a little bit difficult to segment. So the image on the right here is the phase evolve with phase evolve applied, and you can see those phase fringes around here are no longer present, and in between the material is there's far less noise in that material as well. So this is the attempts at doing a very simple excuse me, doing a very simple segmentation. And you can see on the left with the FDK, it's much more difficult, and some of the material in between is accounted for, so that won't be entirely accurate. On the right with the phase evolve sample, you can see that the segmentation has only identified the actual wood structure that's around the surrounding material. So this is really what phase evolve can offer you over what standard reconstruction can offer you for samples with small density differences that you're trying to highlight, but you also want to remove the artifacts that are caused by phase propagation contrast imaging. Okay, so those were the two non-AI reconstruction techniques. So now we're going to move more into the actual artificial intelligence part of the Advanced Reconstruction Toolbox. So we'll start with Deep Recon, or Deep Recon Pro, as it's now known. So what is Deep Recon? So if we think about the traditional method that we use to reconstruct images, it's called FDK. So I can't remember exactly what that stands for because it's a German term, but what it really means is filtered back projection. So this is using just standard algorithms to reconstruct your data, and it has been very good in the past, and is still a perfectly viable technique, but it does come with some limitations. So you need quite a large number of projections in order to avoid things like angle limited artifacts. And you do need longer exposure times as well to make sure the images the projections you're getting are as good resolution as possible. So both of these things can contribute to the fact that you need to collect a lot of data for FDK to produce good results. But obviously, people have lots of things to scan, there are lots of customers to serve. So this isn't always, sometimes things need to move a bit quicker. So the Deep Recon Pro basically replaces the FDK with a convolutional deep learning neural network. So it can take a lower number of scans or even the same number of projections depending, and it puts it through the Deep Recon model, the neural network model, and out of the other side, you get a 3D reconstructed volume with low noise and high image quality. So it's this method tends to be much better for image quality, no matter the slices you use, which I'll explain in about a slide's time. So you can get things like faster scans, and especially for things like semi-repetitive workflows, you can really start pushing the increase in speed or the increase in throughput that you can get from this technique. So again, this is just highlighting the limitations really of FDK reconstruction. And really what I wanted to highlight in here is this graph here. So the higher the image quality that you want, the longer your scan's going to need to take. And then obviously once you're reducing that time, your image quality is going to reduce significantly, and any sort of subsequent segmentation on these faster scans using FDK is going to be quite challenging. So this is a very basic look at what a convolutional neural network is. So this is the type of network that Deep Recon uses. This is not the be all and end all. There's a lot that I won't have been told about the inner workings of Deep Recon, but this will help give you a general idea to how this works. So the first bit that we have in the convolutional neural network is we have this series of convolution and pooling stages. So during the convolution step, we have a weighted kernel that scans across the pixel data for each slice. And that can be changed depending. So that's when the model's learning, it can change how it's applying the kernels and what weights it applies to the kernels to convolve your data and reduce its size. And then the pooling is a little bit simpler. It's pretty much about just reducing again the size of your data. But throughout this whole process of convolution and pooling, what it's doing is it's keeping the actually useful bits of your information. So you're not losing any important information. It's just reducing it down to a size that is much more manageable for the neural network, because previously, without these steps, the amount of data the models were having to deal with was so large, which it just meant that building things like the models and reconstructing took very, very long time. So by reducing the data without losing any essential data, these networks can operate much more quickly. So once it gets to this end here, it then enters the hidden fully connected layers, and this is where it will apply the different weights to the different connections, and then it will output the reconstructed volume. So Deep Recon itself has two primary modes. The first mode is probably one that people will associate most with a deep learning network. So with all deep learning networks, you need a training data set. So the first bit of this workflow is that you capture a training data set of your sample, and then you use this data set to train the convolutional neural network. So you have a model that you can then apply to a future data set. So if you have so this is probably most useful for where you have either a semi or fully repetitive workflow. So when you have really, if you have more than one sample that's quite similar, this is what you'll be using this mode for, because then once you've got that training data set and you've trained the model, you can then capture future data sets, and you can then reduce your throughput on those future scans. So you capture the data set, You then apply your convolutional neural network or deep recon model, and then you get your reconstructed volume at the end. But there is another mode that deep recon can operate in. So not everybody has those methods where you're going to be repeating samples over and over, or even just a few of the same ones. Quite often you'll just want to do a single scan. So can deep recon still be useful there? The answer is yes, in short. So we would operate in what we call image quality mode. So this is where you capture your data set using the Versa or Context or Ultra, whichever one you've decided. Then you then have what we call a self-training version of deep recon. So with the data that it's inputted, it sort of self-trains on that data set, and then it outputs a reconstructed volume. So it reduces the overall workflow time, if you know what I mean, because creating the models to forward apply, creating the model to forward apply does take some time, depending on how much input data you are putting into the model. It can maybe take somewhere between 1 to 2 hours to create that model. But with this way, you can just do this all on one data set, and with the improvements that you can get, it's still very much worthwhile applying deep recon, because Versa scans can take a long time. So any improvement you're getting in things like throughput and image quality, you're probably more than making up for that in the you're more than making up for the time needed to make the model in the reduction and improvements that you're getting in scan time and image quality. So this is a very quick video just to show you how easy it is to set up deep recon, because we don't want this to be difficult. You don't need to be an expert in artificial intelligence to operate deep recon. So we're starting with an Xradia Ultra data set here, which you can see in the top left. So all you need to do on the Scout and Scan model, software, is change the recon type to deep recon. And then you go into your tab at the top here, which is deep recon settings, which you will have if you have the software. If you already have a model available, they will be saved in this drop-down menu here. So if you have a suitable model, you can apply it. If not, you can go here and train your model on the data set, and you can choose between the scan time reduction and the image quality modes. So the scan time reduction will just be a drop-down between 2 to 10x, depending on your sample. And then once you're happy with that, you can just click go. And then once the model is trained, it will then add that model into your available deep recon models. And then if you have the right data set, all you need to do there is, well, usually click the final reconstruct button at the bottom, but you will always want to do a preview first to make sure that your sample has been well aligned. Because obviously, as with any data set, to get your best reconstruction, you need to do things like your center shift to make sure the reconstruction is good. And you can see here that that what they've chosen is very suitable settings, and they can then move on to the final reconstruction. So whilst building the model can maybe take, maybe an hour or two to build the model, actually doing the final reconstruction takes a matter of minutes. It's very quick, and the hardware supplied by ZEISS for deep recon is very capable. So actual reconstruction can be very, very quick indeed. Okay, so on to some examples of deep recon now. So the first example that we have here is a ceramic matrix composite. So what they did here is they did a standard reconstruction with 3001 projections, which took a 9 hours total time on the Xradia Versa. They then reduced the number of projections in the reconstruction to 301, which was a total scan time of 53 minutes. And then on that same data set, they did a Deep Recon Pro reconstruction. And you can see here that actually the Deep Recon Pro reconstruction is equally good, if not maybe slightly better, than the 9-hour scan time standard FDK reconstruction. So in this case, it was around about a 10x improvement in throughput using the throughput mode of Deep Recon. So this is obviously a very nice example because it's a very high increase in throughput. The amount of increase you'd get in throughput mode will very much depend on the sample, as we'll see in the coming slides. But this really shows that for certain samples, you can really get a very high throughput improvement without sacrificing the image quality that you get from the reconstruction. So this next one is a pouch cell battery, and this is actually done using the image quality mode. But what they did is they took a quarter of the projections from the standard reconstruction. So you see here the total scan time for this sample was 6 hours, and you can see with the FDK reconstruction, it'd be very difficult to do any reliable segmentation on the actual grains of the cathode material here. Whereas with the Deep Recon Pro, doing the same reconstruction, we can actually see the individual grains much more clearly, and that would be much easier if you did want to try and apply a segmentation. The other thing that you'll notice is that in the in-between material here, you can see that the background sort of microstructure is just it's washed out in the noise in the FDK reconstruction. Whereas in the Deep Recon Pro, we can start to see some of the actual microstructure in this segment of the battery here. So it really can help bring out an extra information that isn't necessarily immediately accessible in the FDK reconstruction. But just, we're showing lots of examples here to show you that this is fully applicable across the board in terms of sample types. So this was looking at image quality mode in particular, but this is another one on an interposer semiconductor package, where again, we've captured 1,200 projections in 120 minutes on this particular sample. Then we've reduced that by ×4 to do a standard FDK, and then we've done a deep recon scan. And you can see that actually here, we've got probably, I would say, a pretty higher image quality compared to even the 120-minute scan for the Deep Recon Pro. It'd be much easier to segment this and do some further analysis on these pores than it would be for the standard reconstruction, even with 4 times the scan. So there's at least, there's at least a 4 times improvement here. This is having a little look at a geological specimen. So this is a gneiss from the Scourie Gabbro rock formation. So we've done an initial recon here, which was a very quick 30-minute scan on a 15mm core. And you can see here for the Deep Recon Pro reconstruction that there is a much less noise in the actual grains, and the image just looks generally a lot sharper compared to the FDK reconstruction here. So even on these very heterogeneous samples, Deep Recon can still perform very well. And then it should be important to cover what's actually new in Deep Recon for this version of ART, and the new bit is that we could apply it to Xradia Ultra data sets. So that's our nanotomography instrument. This example here is a seed, and what they've done is they've actually tried to see how far they could push Deep Recon for this. So they've done a baseline scan, in which case you can already see that the image quality sort of aspect of Deep Recon gets you much better data sets. But then they've tried to do a 2x, 4x, and even a 10x reduction. So you can see here on the 10x reduction for the Ultra, there's nothing much you could do with that data set using standard reconstruction. But the Deep Recon Pro, whilst not quite up to the standards of the previous Deep Recon models, still actually gives you a workable data set. So if speed is really the issue, you could maybe end up sacrificing a small bit of image quality, but still get a very nice data set. So it's definitely very applicable to Xradia Ultra data sets as well. Okay, so that covers Deep Recon. So the final bit I'm going to cover today is looking at probably the biggest new bit for ART 3.0, which is our Deep Scout software. So what is Deep Scout? So usually you have a trade-off between resolution and field of view. And this is a challenge for any microscope, yeah? So in this example here, you can see that we have a low resolution scout on this PCB. And then we have a high resolution zoom. But if we wanted to look at the whole board in high resolution, we would have to do, in this case, at least 9 high resolution scans and stitch them together, which would be a lot of work. It'd be very complicated, and obviously there's not many instruments that are going to have that much free time to do that on a sample. You're going to need to probably choose an area of interest and hope for the best. So what Deep Scout allows you to do is take a single large field of view, a single zoom, and then using the deep learning neural network of Deep Scout, we can then apply that across the whole volume to recover the resolution across the large field of view. It's one of those things that always sounds too good to be true, but do stick with me. So this is how it works. So you have your large field of view sample, and you have your high resolution small field of view sample. And what we do, so if any of you know super resolution microscopy on the light microscopes, how that works is that you basically have a calculated point spread function that you can apply to the low resolution data set in a super resolution microscope. We don't quite do that. What we do instead is we train the neural network to learn the point spread function between the two data sets. And then once it's learned that, it can then infer to the rest of the data set that you have, rest of the large field of view data set that you've acquired. So this is just an example that we have here. So this is a Deep Scout example in a smartphone control board. So we did a small scout in a central region of this board, and then we applied Deep Scout across the board. So it's not going to play the video, which is a bit of a shame. But what we would say is that you can get up to 125 times the volume gain of the same resolution that you would be able to achieve on your high resolution data set. So that would only require one high resolution scan. So much faster than doing lots of subsequent scans. So really, I can say all of that, but if we can't prove anything, then it's not very useful. So we'll have a look at some examples now. So this is an additively manufactured lattice. So what you can see in the center here is you can see the large field of view, low resolution data set, and you can see where we've acquired the high resolution data set in the center here. And then these reconstructions are done across the whole low field of view, large field of view. Keep getting this confused. So you can see here the standard reconstruction using a voxel size of 7.93 microns. And then you can see the Deep Scout restored whole field of view at about half the pixel size per voxel. And you can see here that the improvement firstly in the image quality is somewhat significant, and that's just due to the deep learning neural network. But you can see in terms of some of the smaller pores that are resolved more thoroughly, Deep Scout volume does that much better compared to the standard reconstruction. So in this case, they've about doubled the resolution that you can get across the Deep Scout restored volume for this sample. And this is just looking, again, this is looking in higher resolution now. So again, what we're really focusing on here is the ability to when you do your quantitative analysis, is the ability to define the pores that you actually have generated in your sample, particularly important for the lattice here, because porosity is always a problem in any metallurgical process, forming process. So always the case with additively manufactured samples as well. But you can see here that the pores are much better defined. There's no sort of smearing across them. So when you come to actually try to quantify the pores, you're going to get a much better data set because you've essentially been able to work across your whole volume at higher resolution. I mean, the one thing that I should point out though is what you'll notice between these two images is Deep Scout doesn't pull out like things that aren't there. So it's not, so if you have like a section like this in your low resolution data set where there's no information about pores, Deep Scout isn't going to just say magically there's a pore here. It's more going to be, you know, where you've got like maybe a small sort of like you know, something here that it would be very hard to segment. You know, you can just see that that's now a much better defined pore on this side that will be easier. So it doesn't produce things that aren't already there. It just puts things that are there into a higher resolution. And this hopefully helps bring that point across. I know this is only one example, but hopefully it helps give you a bit more faith. So you can see here that the CB here, or the large field of view low resolution data set, we counted the pores in this small section here, and the count was 178. And then in the high resolution data set here, we also did a pore count, and you can see that we obviously get a lot more because we can look at a lot smaller pores with the high resolution data set, 452. And then with the Deep Scout applied volume, you can see that we don't quite get the same number of pores as the high resolution data set, but we get very close. So it's not absolutely perfect, but it will speed up your workflows and can give you very good statistics. So there are a few pores here and there. It's not quite been able to pick out because they just weren't visible in the low resolution data set. But everything that was there to be picked out, it has done. Looking at a few more examples now. So again, looking at a pouch cell battery in this case. So we have a low resolution scan here, which is done. I have a feeling that voxel size is wrong there. Oh no, so 0.5 micron per voxel for the low resolution scan. And again, we've about doubled that for the high resolution scan. So you can see a lot more in detail the actual microstructure in the anode and cathode materials. And then this is the Deep Scout volume. So they've taken this high resolution scan and applied it across the whole volume. So you can see that we've actually managed to take a lot of this microstructure that wasn't necessarily visible before in great detail in the low res scan across the whole of the sample, and the actual grains in the cathode material here are much more easily visible compared to the low resolution data scan. But again, you can see even from like the lines and things that are over here towards this side of the cell, it's it's not bringing stuff through that wasn't already there. This is it applied to a limestone sample in this particular case. So again, low resolution scan on the left, Deep Scout volume on the right in this case. So we're not showing the smaller high resolution data set. But you can see here that we've probably about maybe reduced the pixel size, or basically increased the data size by about 3 for this right image. And then you can see here the improvements that you get with the Deep Scout volume. So you can see there's less noise in the data. You can see that the actual difference in phase density, it's not quite such a bright spot. It's evened that out a bit. And some of these smaller sort of cracks and grains that were visible. So you can just about make this one out in the low res scan, and you can see that much more clearly. And this section here over here as well in the Deep Scout volume. So it's only bringing through stuff that was already just about there, and it's making it much more defined, much clearer in the Deep Scout volume. I think the final slide to show you is this one done on a soybean flour. So this is very nicely done by Keith Duncan over in the United States. And so one thing to understand about Deep Scout is that obviously what you're essentially doing on your volume is you're reducing the voxel size to get your high resolution. And the important thing to know about that is that the size of your data will increase by the cube of the differences between your voxel size. So so let's say, so in this case we have 2 and we have 0.75. So just over, so we've just over halved the voxel size, which in effect means that it'll be, I mean, to make the maths in my head easy, 2 to the power of 2. So the volume, so if we wanted to reconstruct the whole volume from the high resolution data set, so to speak, we would increase the size of that of the low resolution scan by about 8 times in its file size. We can push that up to around about 5 times, depending on the sample. So you can have a difference of 5 times between the high resolution voxel size and the low resolution voxel size. Anything more than that, and the models do start to struggle. But obviously, do bear in mind that 5 cubed is 125. So if you want to really push that, your data set will be 125 times larger, which is why in this particular case, when they've gone to do the deep scout high resolution or apply the deep scout model, they've selected specific areas to do this over. So rather than do it over the whole sample, which would certainly be possible, but would make a very large data set, they know that they're interested in these bits and these bits in the center here, and that's where they've applied the deep scout volume. And you can see the extra resolution that's brought in by deep scout into these bits compared to the standard FDK reconstruction. You can see a lot more of these small white bright areas compared to the standard reconstruction, and the background is much more better defined in the deep scout images as well. Okay, so that's been a lot to get through. ART is quite a chunky topic, but hopefully I've given you guys a flavor of what the Advanced Reconstruction Toolbox can do for the ZEISS Xradia platforms, from the Context to the Versa to the Ultra. So we have Deep Recon Pro, which is our deep learning reconstruction that can be used for increasing throughput and or image quality. Deep Scout is essentially super resolution on the X-ray microscopes using deep learning to basically generate a point spread function. Phase Evolve is our first non-AI technique, which is used for the removal / reduction of phase fringes for samples with low differences in density that you're trying to highlight. And then Mars is good for almost the opposite reason. So when you have a very high density part in a low density material that causes artifacts, Mars can help reduce those artifacts. Okay, so that brings me to the end of my presentation. I think I've just about stuck to time. So what I will do now is I will have a quick look in the chat box and I'll see what questions we have. Okay. So we have some comments. Okay, so let's have a quick look at the questions. So the first question is, can you give us more details on the neural network Deep Recon uses? So the details that I gave today were pretty much as detailed as I know. What I would say is, if there's anyone who does want to know a bit more about the actual model itself, please do get in contact, and we can arrange a specialist to talk through the ins and outs of the Deep Recon model with you. But just to reiterate, it's a convolutional model, so it's basically taking your data set, it's reducing its size in the first step to bring it down to something more manageable for the model. And then it's using a closed network, fully connected closed network to then make inferences on your sample and then generate a 3D data set. So hopefully that answers your question. Next question from Anthony. Could you please provide some more information regarding the Deep Recon CNN approach, i.e., is it applied on the radiographed or reconstructed images? It is not very clear. Okay, that's a perfectly valid question. So the CNN approach is applied on the radiographs as they come in. So it's not applied on the reconstructed images. Apologies for not making that entirely clear on the slides. Okay, so next question from Matt Divers. And with deep scale, are you training based on projection data or reconstructed data? Again, a very good question that I should have made more clear in the slides. So the deep scale, so what you have for the deep scale is you do have reconstructed data sets to begin with. So you'll have a high resolution reconstructed data set and a low resolution, and you feed those into the model, trains the model, and then you can use that to apply to the different areas that are in your sample. Next question, is the deep recon CNN a self-supervised approach, i.e. do the network weights update during reconstruction? So the self-supervised approach is applicable to the image quality mode, but not to the throughput mode. So I mentioned there were the two different modes. Yeah, the first one is the image quality is self-supervised. The throughput mode, sorry, is not. Okay. Next question from Michael. What's the difference between X-ray microscopy and X-ray microtomography? So essentially the difference between those that I showed today is X-ray microtomography, or X-ray CT, I guess as it's called, is just using a single method of magnification, which is called geometric. So basically, if you want to improve the magnification, you have to move your sample closer to the CT source. With X-ray microscopy, you are adding a second step into the magnification workflow. So you still have the geometric, but you also have an optical magnification stage, where it means that because with the first one, with geometric, if basically you can only get as much resolution as you can get the center of your sample towards the X-ray source, and with big samples, you can only get that so close. So the middle is always going to be less resolution. Whereas with the two-stage magnification, you can have larger samples, or you can have your sample further away from the source and still get sub-micron resolution. So hopefully that answers your question. If you do want more details, please do feel to reach out and we can have a specific conversation. Okay, just to clarify, I think final question, and then we can probably call it a day. Just to clarify for Deep Recon, it is applied to projection, but the reconstruction is also completed by the CNN, or is it essentially denoising the projections and reconstructing via another method? Yeah, so you do create the models, and the reconstruction is also completed by the neural network. Hopefully that answers your question. Okay, so I think that's the end of the questions. Thank you all very much for listening to the presentation today. If there are any further follow-ups to the questions, I believe all of my details are on the link that you guys logged in with, and you can reach out to me directly, and I'll do my best to forward you to the best location or the best person to answer the questions if it's not me. But yeah, with that, I'd like to thank you all for your time, and we will close the session. So thank you very much.